Okay, so we're going to do 3 examples here. These are going to be quick and dirty, and there's not going to be any take 2. So first off, we'll read the question. A 1.5 centimeter object is placed 6 centimeters from a convex lens with a focal length of 2 centimeters. What is the height of the image and how far away is the image? So let's write out what we have. The 1.5 centimeter object, that is the height of the object. So really, HO is always just going to be the sort of the size. Doesn't really, it's not like we're measuring how tall someone is every time or something like that. Place 6 centimeters from a convex lens. That's the distance of the object. So it's always the distance of the object from the lens is DO. The focal length of the lens, this is where all the light rays will converge if they're parallel. To start is 2 centimeters, and I'm going to use positive 2 here because this is a convex lens. And so we're looking for the height of the image, which is really just the image size, so how big the ant would look if you were looking at it under a magnifying glass or through a telescope or whatever. And how far away the image is. This is where the image would appear. You may have noticed sometimes when you look through a magnifying glass, it sort of looks like the larger image is further back. So where the image appears is the DI here is what we're looking for. So we'll do the math second. We'll do the diagram first, and we'll see how we do those. So first off, you want to draw yourself a straight line, which we'll call the principal plane. This is sort of just cuts the middle of the lens. Now the lens, you can draw it really any size you want. Because this is a convex lens, I'll draw a convex lens. But if you didn't draw it big enough, sometimes it happens, you can just extend it down afterwards. It doesn't have to be too fancy. And since the focal length is 2 centimeters, I could measure out 2 centimeters, and actually that would make the diagram, you could actually measure these out in the end, but I'm just going to do this as a rough sketch is all we really need to do. So I'll say that that's 2 centimeters on this side, and because lenses, these are symmetric lenses, it'll be the same on the other side, so the focal length is on that side. It doesn't really matter which side we're on here. So we put those both on there, and then since that's supposed to be 2 centimeters and it says it's 6 centimeters away, I'll make something up and call the object, we'll say that that's 6 centimeters away. So that would be the distance of the object. So this is supposed to be 1.5 centimeters. Again, if you draw this to scale, your diagram will actually measure these out, but we'll do the math to find that out. This distance here should be, again, we're just drawing this as a rough sketch, but that represents 6 centimeters. And so let's see where the image would appear in this case, where you'll notice that DO, the distance of the object, is greater than the focal length, so it's further out than the focal length. Okay, so first thing you do is you draw a straight line, and this represents light coming from the object, either being reflected off or coming from the object itself. It was like a candle or something, and it hits the lens. So when it gets to the middle of the lens, any parallel light will be bent via refraction, which we already talked about, towards or through the focal length on the other side. So you can see there's one. That would be the path of a beam of light coming from there, and we'll see this in class after the break. And the second thing you do to figure out where the image is going to be, you'll notice I draw a little arrow here. That's supposed to be the someone's head, or I don't know, the top of a candle or something like that. We draw a line through the focal length on the other side here, or on the same side as the object, to the lens, and when it gets to the middle of the lens. Now, because this is sort of the opposite, where we went parallel and then that will cut through the focal length on the opposite side, if you go through the focal length on the side of the object, well, what comes out then, it gets bent to be a parallel line on that side. Where these two rays cross is where the image of the top of the arrow would appear. And you'll notice it's upside down in this case, and that's what you should get for this sort of scenario here. They'll always be upside down. You may have noticed that if you were to look through a telescope, although there's a couple of lenses in there, it often inverts the object. And again, we'll play around with that and see that in some other cases. So this is the ray diagram, or the lens diagram for this setup. So we can see here, just judging by this, that the height of the object It looks like it's going to be slightly less than the height of the image is going to be slightly less than the height of the object if I drew this all relatively properly, but we'll see here. So let's do the math. So I want to know what this is, the image distance, that's di, and I also want to know the height size. So to use the thin lens equation, we go 1 over f equals 1 over do plus 1 over di, or opposite. I think in my notes I have it 1 over di plus 1 over do. Sometimes it doesn't matter. You can interchange those things. We know this, and we know this, and we're looking for that. So let's put those in. 1 over the focal length is 2, and again we use a positive 2 centimeters when it's a convex or converging lens. We know the distance to the object, that was 6 centimeters. But what we don't know is the di here. So we're going to have to do sort of some rearrangement here, which I know everyone loves. In this case, then, you might want to look at this, oh, it's all ones on top, so why don't we just, like, deal with the 2 and the 6, flip everything over, and we can find di pretty easily. Fractions do not work that way. These are denominators, so remember when you're adding and subtracting fractions, you need to worry about common denominators and things like that. So first off, though, we want this by itself, so let's get rid of that by subtracting 1 over 6 on this side, 1 over 6 on this side. Remember, we're dealing with fractions here, so we can't just deal with the 2 and the 6. We get 1 over 2 minus 1 over 6 equals 1 over di. Now, if you don't remember how to subtract fractions here, adding and subtracting fractions, you might be tempted to say, oh, that's minus 4 on the bottom here. No, it is not. These have to be treated as a number itself, not a 1 on top and a 2 on the bottom. So we need to find a common denominator here, which will then help us find di. So you can turn these into decimals. Sometimes that's easy, and that's what I did in my notes, but it's not the best way, especially when there's irrational numbers or other weird fractions that don't work out so easily. So here I will find a common denominator. It's going to be 1 over 2 is the same as 3 over 6 minus 1 over 6 equals 1 over di, which means we get 2 over 6 equals 1 over di, and now we can cross multiply to get di, or you can just flip them both at this point. 2 di equals 6, divide out the 2, divide out the 2, and we have the distance to the image is 3 centimeters. 3.0, I guess, if I'm being somewhat careful. So you'll notice in my diagram too that the distance to the image does look slightly smaller, and again, because this isn't drawn exactly to scale, it doesn't quite look like it's 3 and 6, but if I had have measured out 6 centimeters and measured out 2 centimeters, so on and so forth, that should measure out to be 3 centimeters. So that's a way to check your work if you want to be really careful with these. Last thing we want to know then is the height of the image, and we use the magnification formula here, which is hi over ho equals minus di over do. The minus sign is important here. You'll notice this image is inverted, it's upside down, and so the height of the object should reflect that. So that's going to be hi, we don't know what it is, over height of the object, which was 1.5 centimeters, that's where that comes in, equals minus 3 centimeters over 6 centimeters. And now this is just a matter of cross multiplication here as well. So 6 times the height of the image equals 1.5 times minus 3, which is minus 4.5, divide out 6, divide out 6, gives us an image height of 0.75 centimeters minus. The minus tells us that it's an upside down image, which is what we should get again in any scenario where this is the case. All right, that's it for example 1.